Yeah, Sai Krishna, you can start.
So, with warm greetings, I extend my warmest welcome to each and everyone invited here. I am Sai Krishnan, doing my second year in the Department of Electronics and Communication Engineering at Chennai Institute of Technology. We are analog beings living in a digital world facing a quantum future. Chennai Institute of Technology, the college, has not left any stones unturned in making its students worthy citizens. The time as a caterpillar has expired and the wings are ready. Yes, it is about transforming life. It's been just 10 years since CIT has stepped in, but the victories of CIT are huge. It is indeed a privilege for all of us to get the opportunity of attending these webinars. To be short and crisp, yes, it is all about Knowledge 4.0. Today, we have our expert, Dr. Sudeb Dasgupta, Professor and HOD, IIT Roorkee, and our Organizing Secretary, Dr. R. Dhanagopal. I feel much pleasure in welcoming you all. Now, I request our Organizing Secretary, Dr. R. Dhanagopal, to give a brief introduction about the session.
Good morning and welcome back all of you for last day of 1 week online FDP-Recent Electronics and Communication Engineering under 4.0 webinar series. This is one of the trend-setting and innovative initiative of Chennai Institute of Technology. CIT established in the year of 2010. Within short span of time, we achieved top 10 positions among 500 plus engineering colleges affiliated to Anna University, Chennai. Webinar 4.0 series going very successful manner under the guidance of our Honorable Chairman, Shri Sriram, the first generation entrepreneur, a well-known industrialist, and the managing director of NK Group of Companies. We have been conducting webinar series under various webinar series such as technical research, innovation, and career guidance webinar series. In addition to this webinar series, we have been also conducting FDP workshops, conferences, and seminars. I heartily welcome our today's expert, Dr. Sudeb Dasgupta, Professor, IIT Roorkee. Welcome, sir. I welcome you all once again, the participants from all over India to the webinar. Hope that you all will have great time ahead. I will call upon Sai Krishna to introduce the today's expert. Thank you all.
Speaking about our chief guest, Dr. Sudeb Dasgupta is the professor and HOD in IIT Roorkee. He has done his PhD in electronics engineering in the Banaras Hindu University in the year 2000. From then, he has been presiding many designations in different firms and institutes. He has also been awarded many honors and awards, which include the expert member in the Global University in the Netherlands, IUSSTF Fellow, University of Wisconsin, USA, and many more. We are immensely pleasure to have you here, sir. So, without any further ado, I request you to take over the session, sir. Please, sir.
Okay, thank you. I think I'm audible to all of you. I will now share my screen and try to give you a brief insight into low power design.
Yes.
Right. So let me go to application window. Can I'm not, my application window have to go, right, Professor?
You just turn on the screen share, sir.
Turn on the screen, just a minute. The screen, okay, turn off the screen, right?
Turn on the screen.
No, my
mic, no, sir.
My video should be off, right?
No need, sir. If any issues in network problem, you can switch off the video. Otherwise, you can keep it.
Right. I'm sharing the screen now.
Yes,
so
sir.
when I go to I need to go to application window, right?
Yes, sir. Yes, sir.
Okay. Nothing is coming in my application window. Can you wait for
First, you turn on your screen, sir.
Okay, just a minute.
Near mic, no, sir.
Yes.
Yes.
I'm turning on the screen, and now I will be. Let me see. Let me turn on the screen, and then I go to application window, right?
Yes, sir. Yes, sir. Yes, sir.
Nothing is coming in the application window.
Just you, at least you first you share entire screen, sir.
Hello. Yes. I'll just share the screen, right?
Yes, sir.
That PowerPoint is not coming in the. Just a minute. I'll just do it once again, and I will come back to you, right?
Yeah,
Let
yeah.
me try.
Yes.
I'm sorry for the problem.
It's okay. It's okay. It's okay. Yeah, fine, sir. Just make
Right.
it.
Now it's.
Yeah, good. Fine, sir. Fine, sir.
Shall I start?
Yes, sir. Yes, sir. You can start.
Okay, thank you, Professor, for the kind introduction. It was a nice opportunity to present my work in front of the student and the staff community of CIT. I thank you on my personal behalf. So this is approximately a 1 hour seminar, and we will be discussing on low power design issues in this 1 hour seminar. Primarily in the area of digital VLSI design, where the power consumptions and dissipations are a major important issue. So the agenda of the talk will be something like this. I will introduce to you the subject, then explain to you what power is all about. Then we have to know how to evaluate power. That means how to evaluate the power in a real sense. What are the various low power design techniques, and then finally conclude my talk. Now, if you look at the slide, you see quite interesting slide here. You see on the right hand side there are two bar graphs or two bar charts, and if you see very closely, your processors, which is basically the workhorse for any IC design, is the minimum unit sold. So the number of units sold for the processor is very small, but the amount of revenue earning by the industry is relatively very high, right? That is what I wanted to show. So if you look at this blue curve here, this blue and this blue, this gives you an idea. Second comes the memory. So if you take the processors and the memory together, it gives you about total more than 50% of the revenue earned by industry. And that's what is written here, that though 2% of the units sold in industry are processors, and there are 6.5 billion processors per year being produced, you still have more than 50 to 60% of revenue being earned from these processors. So, therefore, the motivation for such a talk is very important. That we need to, therefore, make these processors energy efficient and have a.
Professor,
Yes,
Mr.
please.
Your voice is not clear.
Voice is problem.
Some noise is coming.
No, just a minute.
Yes.
I'll switch off my AC then.
Yes.
Is it better?
Yeah, now okay.
Okay, fine. Sorry for this trouble.
It's okay. Thank you, sir.
Okay, shall I continue?
Yes, sir. You can continue.
Okay, so that's what the current logic is, that we need to therefore focus on processors and memory and optimizing the same to do that. Now, if you look at the trend of power, and this is on the x-axis you have the year, and it is taken from a paper in 2003, and if you look at the y-axis, it is the amount of power being consumed by the chip. And as you can see, by 2020, which is we are currently there, you will be actually producing 1,000 watts of power on chip, right? And that's the major problem area where the trend of the power is going. That maintaining or having such a heavy power is detrimental to the functioning of the processor. That you need to understand or appreciate this. If you look very carefully here, Pentium 4 was developed around 2000, 2005, 2006, and the power which it was giving was approximately equals to 100 watt. We do have now Intel's high-end processor, which gives you a very heavy power, and that's the problem area which people are facing. If you look at the power density, which is basically meaning the power per unit area of the silicon chip, then another interesting thing comes out that if you look very carefully in year 2000, it's a bit old data, but the trend continues. And as you can see, this if you don't have methodologies to reduce power or cool down your chip, then the power dissipated in a chip will almost reach the sun surface power density, which means that you will be actually talking about 10,000 to 50,000 watts per centimeter square of power being emanated from the chip. Of course, that is not a good idea, because what happens is that with such a large power, you have a problem of when you have large power, you have a problem of the wafer getting more and more heated up. And when the heats up, when the whole silicon heats up, then
Professor, sorry to disturb again.
yes, please.
Again, noise
Yes,
is
please.
coming. Yes.
I've told them to stop it. It's just coming from the side building.
Yeah.
Right. So this is the problem area of power. So you will have to methodologies to reduce power density in a silicon wafer. With this knowledge, let me give you the basic idea of what power is all about. So energy, this you have been studying from class 11th and 12th, so I need not any stress part of it. But if you look very carefully, energy is measured in joules, and it's a measure of ability of a system to do work and produce a change. So as you can understand, no work is possible without energy. What is the unit of power? It is basically watts or kilowatts, and this is basically energy per unit time. So basically, we are looking into the fact that I can produce a large energy over a large time, but then my power will be low. But I can produce a large energy over a small time, which will make my power go very high, right? So power is basically per unit time data, whereas energy is the total amount of ability of system to do work, right? So it's energy per unit time which we are looking into currently in an IC design. What is the meaning of average power? Average amount of power basically means that the amount of energy consumed per unit time, and that's the average power which we see. What's an instantaneous power? That's quite interesting. Instantaneous power is as T tends to 0, E by T, that is how I define instantaneous power. Energy by time as T tends to 0, which means that, let us suppose, I'll give an example. Let us suppose I give a transient pulse, right, from 0 to 1. Input pulse is 0 to 1 in a transient fashion. I just need to find out how much amount of power the chip has actually consumed while the input has gone from 0 to 1. Just that transient. That will be defined as the instantaneous power, right? And that instantaneous power you need to go on adding as you go on adding other parts of the system. So as I discussed with you just now, therefore, power is equal to, as you all know, is voltage into time. Both are obviously time dependent. Voltage into current, both are obviously time dependent functions, and therefore energy is equals to power into time, as I discussed with you. So it's basically voltage into current into time, right? Which means that in our, from CMOS circuitry point of view, those who are new to this area, they will understand. Basically, therefore, energy primarily means power into delay. Which means that, say you want say you want to add two numbers, right? You want to add two 4-bit numbers or 2-bit numbers, right? Then the total amount of work done, right, will be same if you choose any architecture. As a result, what will happen is your energy will always be the same, right? But if you are doing with a very fast processor, your delay will be reduced, and therefore the power will be high, and that is very. Hello,
No, sir, you can say, you can continue now. Okay, we got you.
can I continue?
Yes, sir, you can continue.
Okay. So can you switch off the mic at your end so that when there's a noise coming from that side? Thank you. So we get power into delay. So which means that a high-end processor with a very low delay will actually consume a higher power, whereas a slow speed processor will work at a lower frequency, but its power requirements will be also low, which means that for a fixed energy for a particular process to be done or job to be done, power and delay, they are just opposite of each other. So if you want to reduce power, your delay will become larger, and your delay becomes larger. And when you are dealing with lower delay, your power becomes high, and that's the problem area which people face. So let me, as I discussed with you, therefore power will be equals to IDT into VDT. VDT is the amount of power supply you are giving to a chip, and therefore energy is nothing but the integral of power from 0 to T. 0 to T is the total time taken to do a particular work, and average power is equal to energy per unit time, and that's what you get. That 1 by T is equals to 0 to T IDT into VDT. Quite interestingly, therefore, the product of current and the voltage at a particular point gives you the overall power system. Now, generally, this VDD which you see in front of you is the DC voltage which is given on chip, right? But current within a chip is a function of many other factors. For example, what is the resistance in the particular area of the chip, and so on and so forth. So the power dissipation, instantaneous power at various points within a chip, right, will have various values. But the overall power will be there for the sum of individual powers from individual point in the chip. So that I wanted to stress from this point. So we have understood therefore. So what is the takeaway from these 5 or 6 slides? That what is the motivation, right? Because we have to have processors and memory which are very power hungry, but they earn about 60% revenue for the industry, and therefore we need to optimize that from the point of power. We also define the problem of power, because as you reduce your dimensions of the device, remember in a FET device, current is equals to proportional to W by L. So if you reduce your L, your current increases. As the current increases, same applied value of VDD, the power becomes very high. And therefore, if you don't do anything, the power will show an increase, and the power density also shows an increase. We have also understood the definitions of power. So let me come to the basic fundamental principle of CMOS. And the CMOS is nothing but you have a PMOS at the top, right? And you have an NMOS at the bottom. Please understand, for this NMOS to get switched on, you require the voltage to be high, and therefore when the voltage becomes larger than the threshold voltage of this NMOS, this becomes switches on, and any charge accumulated at CL gets discharged to the ground. Similarly, when my input voltage is low, my PMOS gets switched on, and my NMOS is switched off, and therefore the charge from VDD accumulates onto CL. Right? This is what is happening in this case. So let me show you. Let me show you the animation here. This is what I am trying to say. That as you try to make your PMOS go high, as you make your PMOS switches on. Hello. Yes. So as the PMOS switch becomes, as the PMOS switches on, the charge from VDD through this PMOS, right, through this PMOS goes to CL, Cl, right? Goes to Cl, right? And therefore the capacitance here gets charged. Cl gets charged in this case. And therefore you see, as you can see here, that the cup was fully filled with charge. As I made my voltage go from 1 to 0, PMOS switches on and the capacitance gets charged, right? And therefore output goes from 0 to 1, right? Now let me come to the next slide. So this is therefore energy consumption is therefore proportional to the capacitive load. Half CV square, remember, energy in the capacitance. So as the capacitive load increases for the same amount of VDD, you have a linear increase in the energy consumption of a CMOS. Now let us come to the point that your output is 1, right? And your input is 0, and therefore you are actually increasing the input from 0 to 1, right? When you increase it 0 to 1, please understand NMOS switches on, and therefore all the charge which was accumulated at the output, it actually falls down to the below side, to the below part. It falls down onto the ground, right? And as a result, you have discharge and the output goes from 1 to 0, right? Just hold on a minute. Hello. Tapi bola, আমি মিটিং আছে বুঝছি, ওয়েবিনার। তাহলে পরে কথা বলো, এখন কথা বলো। তাড়াতাড়ি বলো। তাড়াতাড়ি বলো না তুমি, এখন আমি পাচ্ছি না, বলো না। না দিই এখনো। না। ঠিক আছে। ঠিক আছে। দাঁড়াও এখন 1 minute হোল্ড করো। I will just come back in 2 minutes. Just 2 minutes. Sorry. শেষ করে তাহলে, হ্যাঁ ঠিক আছে, হয়ে গেছে, বুঝে গেছি। এবার কি করতে হবে? তখন ফোন নম্বর দিয়েছিলাম না তোমার? আমি ঠিক আছে, দেখে নেবো, আমি দেখে নেবো। ঠিক আছে, ঠিক আছে, ওকে, ঠিক আছে। Sorry, I had an important call to attend, and I'm extremely sorry. So let me start here now. So I get output goes from 1 to 0, and therefore the output suddenly falls to 0, right? So this is what is happening. So energy is only consumed during the input cycle going from 1 to 0, and the energy is left or is dissipated when the output goes from 1 to 0. Now let's see what happens. Quite interesting. Let us suppose your PMOS, right, which is the pull-up transistor here. This one has got a larger width. W/L ratio is larger, right, in this area. Let us suppose this area has got a larger W/L, which means that its current drawing capacity will be larger, because remember, in a FET device, current is always proportional to the aspect ratio W/L, which means that if your W is larger, this PMOS will be able to pull larger amount of charge from VDD.
Sir, excuse me. Sorry to disturb you. Your voice is breaking.
Please, no problem.
Voice is breaking, sir. Your voice is breaking.
Oh, is it? I'm okay. Hello, Professor Malti.
Yes, sir.
No, is there a background noise or the voice is breaking?
While talking, your voice is breaking. Now you carry on, Professor. I can check now.
Okay, fine. Let me do that. Fine.
Yes.
Thank you. So what you can see is that as my width increases, the current carrying capacity increases, and therefore I am able to transfer larger amount of charge from VDD to CL in a shorter time, and therefore you see the output goes very fast at the top. You see this slope is very fast, whereas the second slope you see here, this one is relatively slow, which means that if I increase the pull-up ratio, W/L ratio, I will be able to go in the output from 0 to 1 at a much faster pace as compared to, in that case, when your PMOS has got a lower W by L, right? Similarly, when your output is high, and then this is what is happening, that when your output is high and you want to go from high to low, then if your NMOS transistor has got a higher width, then I will be able to discharge faster, and therefore high to low delay will be lowered drastically. Now you see, please understand, I am not changing the capacitor, I am also not changing the voltage. Therefore, my half C into VDD square, which is the total energy, is still the same. So my energy is still the same, right? But inverter 1, which is this one, the top one, is much faster as compared to the lower one because the W by L ratios are higher, right? Though it is higher, which means that if I have a higher width, a larger width, my speed will be faster, right? That is what it means. But you see the fallback. If you have a larger device, your area is also larger, right? Not only your area is larger, your capacitance will be also larger because it is epsilon A by D. Remember your capacitance. So your A is large, which means that your capacitance is large. When your capacitance is large, your energy is also large. So the cost you pay is basically in terms of energy, but the gain which you get is in terms of speed. So you see that your a large size device will obviously consume a larger power, but at the cost of a higher speed also, as I discussed with you earlier, right? So these are the first approach and second approach. If you look very carefully, in the first approach, the power is high, but the time is small. Whereas in the second approach, the power is low, but the time is very, very high, right? But the product of power into time, which is energy, is same for both the cases. So if you look at the shaded area here and here, at the second graph, below, they are exactly same area, which means that the energy consumed is exactly the same. But in the first case, you consume same area at a lower time, and therefore power consumption is higher in the first case as compared to the second case, and therefore you see the height is higher in the first case as compared to the second case, right? As I was discussing with you, energy is the area of the curve, and that is the same exactly the two approaches, which means that I can have two designs, digital design, having the same energy output, but one having a higher power and another having a lower power. And therefore, I was coming to the fact that energy is equal to power into time, and therefore it is basically power into delay, which we define as energy. Right? That is what we have been discussing for quite a long time now. This takes care of our basic understanding of power matrix here. Let me come to the next slide. Right. So therefore, what is the problem area which you face? The problem area which you face is that your battery life is therefore limited, and therefore it sets limits on the amount of battery. Also, your peak power is you need to reduce it. But the problem is that if you want so therefore any layman can understand, even a basic physics student can understand that if you want to reduce therefore the power, a best way to do is that you reduce the value of VDD, right? Because your voltage will reduce drastically, and as a result, as the voltage reduces drastically, you end up having a lower VDD. But when you have a lower VDD, right, certain issues crop up. That is that the signal noise margin gets impacted. Your noise margins get reduced, which means that as you lower your VDD, the IC, digital IC, is now more prone to noise. So your noise will increase when you have a lower VDD, and that's the cost you pay for it, right? So we define new terms, two new terms. One is the power delay product, which is PDP. So it's power into delay, and where P is the power and TP is the delay. And you have an energy delay product, which is basically the product of PDP and TP. So therefore, if you look at EDP, it is basically power into TP square, because one TP is coming from the first equation and another TP is coming from the second equation, right? And therefore, you have at the same power. Now you see, if you look at the energy delay product, right? If your TP is large, right, or TP means basically your propagation delay is large, and it's basically a parabolic function, square of that, remember? As you can see here, therefore, your EDP depends upon delay in a parabolic parabolic fashion, which means that if you have, if say you increase the delay of a IC by twice, then your energy delay product will actually increase by a factor of four times. So if your TP propagation delay increases by twice, your EDP will also increase by 4 times, right? And that's quite an interesting area you see. Whereas a power delay product is a linear function of TP, which means that if your delay increases by an hour or so, your PDP also increases by the same amount when you do a power delay product. So energy delay product is therefore more sensitive to the variations in the value of TP. Right? That is what we are getting from this whole idea. Let me therefore come to the next section. So we have finished with understanding of power. We have understood what power is all about, what is the motivation of power, how the power is generated in a simple static CMOS circuitry. And now we will be entering into the mode that what are the various parameters of power, or where does the power actually go. So they're divided into 3 parts. The first part, as you can see, is the dynamic power dissipation. The second is short circuit current and leakage. So we'll take each one of them individually and see what are the advantages of each one, or what we understand the physics of the whole thing. So dynamic power dissipation is primarily because of regular charging and discharging of the capacitor, right? Because you see,
Professor?
on a load capacitor.
Excuse me, Professor.
Please.
Professor, sometimes the audio was very clear, but many times we are getting air sound. I think air from fan or from window. I think we are getting.
Just let me switch off my fan. Maybe let me then. You please check.
Sure, Professor. Can wait.
Sure.
Yes.
Okay.
Participants, please wait because the audio problem will be rectified. Please bear with us.
Hello. Can I start?
Yes,
Is it
yes.
better? Well,
Fine, Professor. You can start.
right. So I have a dynamic power dissipation, which is basically charging and discharging of the capacitor. And we have short circuit. I'll explain to you, and leakage also. So there are 3 power dissipations. So let me explain to you what is dynamic power dissipation. Dynamic power dissipation is primarily the power dissipation which happens by virtue of the charging and discharging of the capacitor, as I discussed with you. You see very clearly when the PMOS is on, CL charges, and when NMOS is on, CL discharges, right? That is what I'm trying to show you here. Now, the formula which is given here is basically P dynamic equals to CL times VDD squared multiplied by P into F. I will explain each one of them individually. You see, you are consuming half CL VDD squared, right? Every time the input goes to 0, right? You're charging the capacitor. Now, in a cycle, suppose I'm giving a clock, and in a cycle there are two 0 to 1 transitions, and as a result, what you will see is you will have half CL VDD square plus half CL VDD square, and if you add those two together, I get CL VDD square multiplied by, see, the probability that the output goes from 0 to 1. Why? Because of the probability when output goes from 0 to 1 is the only point when you're consuming power from the VDD, and therefore you have to multiply that with power. Why you multiply with frequency? We multiply with frequency because we need to see how many such type of 0 to 1 transitions are taking place in the output. So if you look very carefully, dynamic power dissipation is a function of CL VDD, the probability of the output going from 0 to 1 multiplied by frequency. Right? I will explain to you later. Don't worry about this F0 to 1. We will come to that later on, but I'll explain to you something known as activity factor. I will discuss that later on. Right? But let us give you a simple CMOS inverter, or let us take, let me say, you take a 2-input NAND gate or a NOR gate, right, using a CMOS inverter. Then I will come to that. I will explain to you how activity factor is calculated. See, not every time you will, only in the case of static CMOS inverter, whenever the input goes from 1 to 0, output goes from 0 to 1, right? Only in those cases, please understand. And it's a sure shot mechanism. But if you have a NAND 2 logic or a NAND 2 input NAND gate or a 2 input NOR gate, you will not find always for a 0 to 1 you will get 1 to 0 in the output, or a 1 to 0 in the input you will get 0 to 1 in the output. So therefore, only for inverter, static inverter, your activity factor will be 1, right? And I'll explain to you what activity factor is all about later stage. At this stage, just keep in mind this part, this formula, CL square P into F. And therefore, as I can discuss with you, and we'll come to that it is basic. The dynamic power dissipation is basically data dependent. So if let us suppose you have large number of inputs are zeros, right? If inputs are zeros, then you are not basically charging. Suppose inputs are 1, right? And input are 1 basically means that when V input is equals to 1, your capacitor is fully charged, and your capacitor is fully discharged, and nothing happens, right? Then you are not consuming any power from VDD really, right? Understand this part. So it is basically data dependent. Let us look at another second point, which is basically short circuit power consumption. See, when your input goes from 0 to 1, what happens is that when it is 0, your PMOS is saturated and NMOS is cut off, right? When it fully 0, and as the input goes from 0 to 2, and when it goes to 1, NMOS gets saturated and PMOS gets cut off. So somewhere in the middle of it, you will get both the devices switched on simultaneously, right? When the input goes from 0 to 1, somewhere in the middle part of 0 to 1 transition, you will automatically have those regions within 0 to 1 transition, wherein you will always have both the devices, PMOS and NMOS, switched on, right? That is very, very important point to be seen. That is the point when VDD is directly connected to ground, and therefore there will be a short circuit current which will be flowing from VDD to ground, right? Now, if your slope of your 0 to 1 input is high, you allow a larger time for the short circuit current to flow, and as a result, the power will be more. Whereas if your input transitions are very fast, you will not allow the slope to be very high. The slope will be really very high, and therefore you allow a smaller amount of time for the short circuit current to be there, and as a result, your power will be low. So simply by engineering your slope of the input waveform, I will be able to sustain either a low short circuit power or a high circuit power. This is because of the direct power between VDD and ground. Now, if you see the formula here, it's VDD, right? Obviously, the voltage multiplied by ISC. ISC is the short circuit current multiplied by P0 to 1 plus P1. Why is it P0? P0 to 1 is the probability that the output goes from 0 to 1, and P1 to 0 is the probability that the output goes from 1 to 0. Please understand, for both the transitions, you will have an input transition taking place, right? And for each input transition, you will have one short circuit current flow. And therefore, every time you see a change in the short circuit path or short circuit current, you add those two probabilities to get the overall short circuit power dissipation, as I have shown in this diagram. Now, what's the leakage power? Well, leakage power is when both the devices are off. At this stage, you need not be worrying too much about it. But when the device is in the off state, you still have some power, which is basically subthreshold leakage. You can have also gate outside leakage, where the current from the gate starts to flow towards source and drain, and therefore even when your device is in the off state, if you're consuming power, that's a bad thing, right? And therefore we need to understand that property in a much more detailed manner. And that's the reason your leakage power consumption is much lower. Is much lower generally as compared to dynamic power dissipation. And as you can see here, P leakage is given as subthreshold. I threshold is subthreshold leakage, which is basically subthreshold current which is flowing, and I gate is basically the direct gate current multiplied by VDD is basically your leakage power current. But let me come to the power equation. You can see here the first equation is a dynamic power dissipation, right? The second one is a short circuit, and the third one is a leakage power, right? And therefore, quite interesting study is there that the dynamic power is approximately the largest factor as of today, but it is decreasing. And the reason for decrease is that you're able to decrease the value of VDD. And you can see that VDD is having a quadratic factor, right? It's the power 2. So if you reduce VDD by half, you will be able to reduce the power dissipation by dynamic power dissipation by 1/4. Right? And that's the major advantage of dynamic power dissipation. Because if you look at the second one, short circuit power, it is very, very small, it's just 10%, and it is decreasing. So short circuit is not a major concern. But leakage power is a major concern because of large amount of subthreshold leakage current is there. So there are three components to the power. Let me again here.
Professor,
First is the dynamic power. Second is hello.
Again, sorry to disturb. Professor.
Please.
Yeah. Your voice is again not audible to us.
Okay. I don't know. Let me change my mic. Then maybe it's a. Let me change. I don't know.
Yes, sir. Just change.
Sure. I will do that. Okay.
Okay.
Hello. Am I audible?
Yeah,
am I audible?
Sir? Yes,
Is
sir.
it better?
Yes, Professor. I can able to hear you.
Great. So let me start then.
Yeah, now you start.
So the leakage power is relatively small, but it is increasing day by day because of the reduced subthreshold current. So let me explain to you now what is an important factor, which is known as activity factor. See, what I will explain to you what does activity factor mean. Activity factor basically means that forget about what is written here. We can discuss that later on. But let us suppose you have input cycle. It's a clock. Let us suppose it's a clock, right? So I will have 0 to 1 and 1 to 0 transitions in the input cycle. And because of that, please understand the power consuming cycle in the output is only 0 to 1. So let us suppose in 4 clock cycles of the input, you get 2 0 to 1 transitions in the output. Let us suppose your gate is such that for an input 0 to 1 transitions, 4 0 to 1 transitions, you just get 2 0 to 1 transitions in the output. Then we define activity factor as 2 by 4, which is 1 by 2.5. Similarly, if there are 4 clock cycles in the input side, right? So you have 4 clock cycles. In the 4 clock cycles, there is just 1 0 to 1 transition in the output side. Then we define the activity factor as 1 by 4, and it is 0.25, right? Which means that the maximum we can have an activity factor is basically 1. When you can have 1, whenever for every input 0 to 1 transition, you have a 0 to 1 transition in output, right? So sorry, every 1 to 0 transition in the input, you have a 0 to 1 transition in the output. You will always consume power, and as a result, you will always have activity factor of 1. So generally, as you can see, therefore, if you apply a clock will have always an activity factor of 1. Whereas if you have a signal with switches once every cycle, then it is 1/2, as I discussed with you, and so on and so forth. Typically, most of the designs, static designs, have an activity factor of approximately equals to 0.1. Typical rough back of the envelope 0.1 is there, which means that what does 0.1 actually mean? That if there are 10 clock cycles in a particular gate, in a particular design, then the output for every 10 clock cycle, the output shows only one 0 to 1 transition, right? So therefore, alpha, which is the activity factor, depends upon the topology of a gate. What type of gate are you using? Are you using a NAND gate, NOR gate for your functionality? So therefore, P dynamic, as you can see, is basically alpha into C into VDD is equal to F, right? And that makes your dynamic power go like this. So what is the short circuit power dissipation? When the transistor switches, as I discussed with you, there's a PMOS and NMOS are momentarily on, and as a result, there is a short circuit current, and therefore dynamic power will reduce if you are able to make your switching times very small, and you're able to switch very fast from 0 to 1 or 1 to 0. So let me come to the, now let us come to the ways of reducing power. We have finished approximately about 35 to 40 minutes of our talk. I explained to you the various power. What is the meaning of power? What are the various power consumption levels? What is the motivation for such a talk? And let me now come into various power design issues. So how can I, at IC level, how can I actually reduce power? So these are the few of the areas in which we do. And that's very simple and straightforward way of looking at it. You see, one best way to do it is to reduce VDD. As I discussed with you earlier also, one best way to reduce is to reduce VDD. As you reduce VDD, your dynamic power dissipation as well reduces quadratically because it's square, and linear and short circuit, and your leakage power reduces linearly. So you have three advantages there if you reduce your VDD. That's the basic, very fundamental principle. But people will ask you, why do you reduce your VDD? Well, you see, why do you reduce it? As we reduce your dimensions of the device drastically, when you reduce the dimension of the device, your channel length reduces, right? It reduces. Now, if you don't reduce your VDD, which is the drain voltage, the electric field starts to become higher and higher within the device itself. And as a result, what will happen is that there will be a breakdown and all those things will happen. So when you lower your channel length, you also lower your VDD, such that VDD divided by L remains almost constant, right? This is known as constant electric field scaling. So when you do a constant electric field scaling and you reduce your VDD and your L, you end up having a lower power dissipation. Another second point is to lower your frequency. So not every time the user will come to you and ask you for a high frequency IC design. I will give an example. Say for example, you are using let us say a simple sensor, right? And you're trying to detect. For example, you've seen in malls and big shopping centers at the exit you have a sensor which is kept there, right? Now that sensor detects whether there is a person is stealing or something from the store. So within the clock you have a transmitter and there is a receiver here. But please understand, not always does have to transmitter and receiver have to work. Only when they come in vicinity they have to work. So for most of the time it is in the sleep state. I don't want the frequency to be very high. I can afford to have a very low frequency design available. Only when the sensor comes in very close proximity to the receiver, your system should get on and some alarm should be there and so on and so forth. So that's one good advantage, an example of a low power design. And therefore, you actually don't require a very high power to keep that state in on state. A simple battery will do. Similarly, you can do what is known as a clock gating. So another methodology is to reduce alpha. Right? There are techniques of reducing alpha. Maybe tight permits will come to that later on. And of course, you reduce the dimension of the device. So when you reduce the dimension of the device, the oxide capacitance reduces, and therefore your capacity reduces, and therefore you're able to achieve a lower power. How to reduce static power? Static power is composed of two parts. Static power is leakage power and short circuit power. So good way to reduce is that use low threshold devices, low threshold voltage devices. You will ask me why? Because if you use a very low threshold voltage device, then your device will get switched on or switched off at a much lower voltage as compared to a high threshold voltage device. Your VDD reduction takes place, and therefore your static power also reduces drastically. And you can also have a stack device. You can have as a low, you can operate at low temperature, but these are easier said than done because these are not practically possible when you are designing a chip. One practical example is that a lower threshold voltage device works very fine. Let me show you the level of optimization, and this is basically coming from an industry perspective. That if you are able to optimize your power at a transistor level, which is the lowest one, then your error in calculating power is the minimum, right? But then, though it is minimum, your saving is not very high. So it's always advisable that if you want the saving to be very high, please achieve at the algorithmic or system level. If you are able to achieve a low power, that will be very good. But then the problem which faces the industry is that you will have a problem of error also, which means that though you are able to save power by maybe 50%, but the error in actual showing you how much power is saved is also as large as the amount of savings which you do. So you have to pay a price for both of them. So typically people are not looking at gate level design and trying to optimize in terms of power level in that area. So as I discussed with you in the previous slide, it is always advisable. The takeaway is that consider low power design from the beginning. Beginning means that exactly you try to have a low power at software level, at algorithmic level, at architecture level, gate level, transistor level, and finally the fabrication level. Right? And we apply one method at a time when we go ahead and do like that for low power design. As I discussed with you just now, power clock gating is one of the issues. Dynamic voltage scaling is another one which you see. Dynamic voltage scaling. Dynamic voltage scaling means when you want that your power should be low, reduce your VDD, and you can operate at a lower frequency. When you want the power to be high, or when you want the frequency to be high, increase the value of VDD. Yes, I pay the price of higher power, so I can have a dynamic management of my voltage in order to achieve a power ratio in that sense, right? So these are the few areas. Let me come to the algorithmic level also. So for example, I will give you an idea. Say you are designing a system which is basically an integer system, and you're trying to add two numbers up to 2 places of decimal, right? And you're adding another number up to 4 places of decimal. Obviously, the 4 places of decimal will be more accurate, but it will be also more power consuming. So what people did for reducing power is that they did an approximation till 2 places of decimal and reduce the power drastically in doing that. What is the cost you're paying? Accuracy. So accuracy will be reduced drastically, will be reduced in a sense. Another good way of doing it, currently people are doing it very large, is known as parallelism or sort of pipeline architecture, which means that you do the work, but then you do it parallelly. And then, for example, as you are aware of, say you want to add four to a number, then you add them all parallelly. Let the carry bit from the previous node come to you, and then you can go to the second bit of addition later on. But if you wait sequentially, you have to wait for 4 times because it's a 4-bit. So LSB plus 1, LSB plus 2, LSB plus 2, and then MSB. Then you have to wait for at least 4 clock cycles to work. But if you do it parallelly, within a single clock cycle, you will be able to do it, and you can reduce the frequency of operation, and you can actually do it properly. So as I discussed with you, pipelining is one of them. Maybe I will not go into details of pipelining. Another good idea which we did earlier, nowadays it is not done, is that you add redundancy, which means that say you have 16 buses for carrying data, then rather than 16 I have 32. So the cost of area So those 16 run parallelly, then it will consume power. But if the alternate buses run data bus, then your power consumption will be reduced, and therefore there will be a minimal data available here, right? So that is what you get from in this case. So you have got data encoding and you have clock gating, and these are the few of the areas in which people. So let me recalculate what we did now, and it'll make you'll understand the whole thing in a much more easy manner, and then we can come to transistor sizing. So now we're coming into that phase where at transistor level, which a second year, third year level person generally goes ahead. What are the various knobs available with you by which you can reduce power? So as I discussed with you, if your W's are large, which means that you have a large width coming into the picture, then obviously, as you can see on the left hand side, the capacitance starts to increase, right? Capacitance starts to increase. But since your W is large, you carry a larger current for the same VDD, right? Therefore, if you want the current to be same, you can afford to let your VDD go down, which means that if I have a larger transistor for the same current to flow, I can afford to have a lower VDD, and that's what we have a lower voltage here, right? Which means that if you want the performance to be exactly the same, then you can afford to lower your VDD. But if you want to improve the performance, you need to improve your voltage, right? Performance when I say, I mean to say frequency. So now let us discuss two important issues. That so what happens is that you have an inverter, right? An inverter is driving another inverter, or a multiplexer is driving another multiplexer, or whatever. Then there are interconnects between two active devices, right? And they have very long lines, copper lines, which carry data, clock, power, everything. Right? But if these lines are very long lines, they will have huge capacitive loading. You understand? Just like transmission theory of your RF microwave. Therefore, you will end up having a large capacitance when your power lines or transmission lines are very high. So in that case, a large W by L of the transistor will be useful. The reason being that in that case, see, in any case, in such a scenario, the most of the delay is, or most of the resistance is being taken by the interconnect. So you can afford to change the W by L ratio of the transistor. Whereas, if you want to make it low power, then you have to have a minimum size devices. So your W should be as low as possible to lower your capacitance. So we learned one thing, that if your interconnect lengths are very large, please go for a larger W by L at the transistor level. If your interconnect distances are small, you can afford to have a minimum size devices with you. The important part, which is known as transistor reordering. I'll give you an example. Say logically you want to have this Boolean expression being done, right? So it's A1 or A2, you have an ANDing with B, and then you have a NAND. So you have a NANDing of that. So all of you are aware of how to do it. What we do is we first design the pull-up. We design the pull-up. So we do we design first the pull-up PMOS. So in PMOS, you can see, since A1 and A2 are getting this thing, or as you can see here, maybe you can look at the pull down first. Since A1 and A2 are odd, they are actually in parallel, and B is in series to A1 and A2. But quite interestingly, if you see, I have two options. I can keep either A1, A2 at the top and B at the bottom, or which is here. So if you see design number A and design number C, B is very near to the output in design number A, whereas B is farthest away from output Y. Right? So that is the difference between AB and CB. That B is farthest away from both the devices, right? And that's what I wanted to keep in mind. Now let us see what we are doing. Let me say, and that's quite interesting, that let us assume that B in the first design, the B switching transition of B is very high. So AB, which is basically your activities, and this is I'll give you an activity chart so if your input B is having the most largest number of transitions, which is basically your 1 million transition per second, then what happens is that if you keep B, if you're able to keep B closest to the output, which means that if you look at design A and B, but B is closest to the output, you actually save maximum savings approximately 19%. Whereas if you keep it in the second case, in the first case, if it is at C and D, you are not saving too much because it is 0.98 and 1, and it is much larger than 0.18 and 0.884 normalized p-dynamic. Which therefore, an important issue is that signal with the highest activity, right? Please understand, signal with the highest activity should be kept closest to the output. That is what we learned from this whole transition or whole issue. Let me come to now explaining to you the transition probability. Let me explain to you. I have a truth table for NOT to gate. This is how I will be calculating alpha, alpha 0 to 1. Activity factor, numerically. So if input A and B have the same input signal, and the probability of them is 1 by. So the probability of P, the probability of A having 1 is 1 by 2, and the probability of B having 1 is 1 by 2, right? So therefore, the output 0 has a probability that 3 by 4, because there are 3 zeros and there are 4 output states, so 3 by 4. And the probability that the output is 1 by 4. I think this is very simple. So probability that the output goes from 0 to 1 will be nothing but the multiplication of probability that output is 0 multiplied by the probability output is 1. So if you multiply 3 by 4 into 1 by 4, I get 3 by 16. So therefore, what I see is quite interesting, that if you multiply, therefore the effective load capacitance becomes 3 by 16, because you multiply alpha with C by L and I get this amount of this thing. So the transition probability is 3 by 16 in this case. Now let me say, I will explain to you another one. Say, so these are the few I showed you for NAND 2. This is for NOR 2, which you see. And then here for OR, NAND gate, AND gate, XOR gate. So simply by knowing the probability of output equals to 0, the probability that output is 0 and the probability that output is 1, I can find the probability of the 0 to 1 transition by simply multiplying the two probabilities. And these formulas are available with you. You just simply put the formulas and get the transition probabilities in this case. Let me come to the second stage, and that is what is known as logic restructuring, right? Logic restructuring, if you see very carefully, and I'll explain to you what I'm trying to say, maybe I'll explain to you, is that let us suppose the transition probabilities of there are two. So let me explain to you. There are two gates. So one is this design structure, which is known as chain, and on the right hand side you see is a tree. So if you look at the chain with having transition probabilities of 0.5 each, then if you calculate the intermediate transition probability P0 to 1 from, so I want to find out from out at W what is the transition probability. I find out this to be 3 by 16. Similarly, at X I found 0.09, and at F I find 15 by 26. I do the same thing for the tree, and I get 15 by 26 to 56 as output for the tree also, which means that for tree, though my output transition probabilities are exactly the same. However, for the tree, which you see in the right hand side, at Z, your transition probabilities are 0.188, whereas it is 0.019 for the tree, for the chain. So the chain therefore has got a lower overall switching activity than tree, but the problem with the chain is that you will have glitches, which tree does not have. Why? Because you see A and B, so there will be some delay of this AND gate, right? So W will be only available when A and B has given its signal and there is a propagation delay. By that time, C will be already available. So as a result, what will happen is that C has to wait till a particular time, right, before W gets available to it in the input side, and therefore there will be a transition, a glitching, and I will just show you the glitching in a detailed manner here. Now let's come to, I will come to the next slide and show you the glitching, but here I will show you the input reordering. Previous case was with the same activity factor. Now if the activity factor is different, then the one statement is that please keep the highest activity factor closest to the output, as we have already discussed. So if you look at the this circuit and the second one, gate level diagram, then the first circuit has got an F of 0.09, whereas the second one has a diagram of 0.0196. Right? So it's 0.0196, which is much smaller as compared to the first one, right? So it's always beneficial to postpone high transition signals back towards output, and that is what the important point is. Now I'll explain to you what glitching is all about, right? I'll explain to you what glitching is. Let me say I have A, B, and I have this two input NOR gates, and they are cascaded with respect to each other, right? Now you see when A, B are both 1, 1, now output will be 0, right? X will be 0, so X is 0. When all goes to 0, right, the output will be switching to 1. But you see, this is the point where the transition takes place. Agree? But so your X goes to, so what has happened is that there is always a delay here. Why? Because initially AB was 1, 0. Now what has happened is both A, B, C are all 0. So there is some delay of this NOR gate, right, which does not allow the X to go to 1, and it only goes 1 after 1 unit delay, which is equal to the propagation delay of the first NOR gate. After that only Z goes to 1, which means that though you think you have given a proper input as 0, 0, 0 and you should get 1 in the output side, you actually end up having a 1 at a much later time, and therefore there is a delay, and this is known as glitching in digital design, right? Same thing is available to you in a case of NAND gate also, and I will just show it to you in this case, and maybe that will be my last or second last slide to give you an idea, and then we can stop here. If you see here, therefore, let us suppose I have a NAND gate, so I've got a NAND chain of inverter, 2 input NAND chain of inverter, and as you can see here, I give 1 to the first NAND gate, and then I give a 0 to 1 transition in the first NAND gate, which means that the output 1 will actually, so if it is 1 and the input goes from 0 to, if it is initially 0, a NAND gate will show 1, but as the input goes from 0 to 1, the output goes to 0, which means that if you look at this black curve here, this black curve, it goes to 0. But since the input to the second gate is delayed by 1 propagation delay of this 2 input NAND gate, therefore out 2 will get delayed by 2 gates here, and therefore you see out 2 is going like to the top, but it is delayed by certain factors. So as I move from left to right of an input of Gen and NAND gates, you have a large amount of glitching taking place because of a large propagation delay, right? And that makes my life difficult in the sense that my power dissipation becomes larger and larger in that case. Let me come to the adder also. The same concept with adder, that if you have a chain of adder here, and then if you give your input from this side, 0 to 1 transition, then my S0, S1, S2, S3, S15, they will be all shifted in time domain to the right. So if you look very carefully, S0 is coming here, S1 is delayed by 1 nanosecond, S2 is coming at 5 nanosecond, and so on and so forth. So it's getting delayed by a certain amount, right? And this is what is known as basically glitching, and therefore it adds power to the whole. So how do you cope with glitching? Very simple and straightforward. Try to make the paths equal. Once you make the paths equal, obviously the delays don't have effect, because you see in the second case, if F1 and F2, assuming they have exactly the same delay, then this and this will have the same value, or will have the value approximately the same time, right? And that makes it relatively easier to handle the glitching. I will not go into details of this one because this requires a good amount of understanding of other things. But I think I will stop here because about 1 hour has been taken. And I will just recapitulate what we did. I gave you a basic idea about the motivation for power. I also gave you the various definitions of power. I also explained to you what power is all about, what are the various components of power, and finally we ended up at transistor level and at gate level. How can you? What are the methods available to you to reduce power? Right. So with this few slides, let me thank you for your patient hearing. Now I am open for any discussion or any questions if anybody wants to ask. Please go ahead. Hello.
Hello.
If
Hello.
anybody has questions, I can answer these questions.
Yes, sir. I
Please.
think if you reduce the power dissipation, what is the basic advantages?
Advantage is that your on-chip temperature does not rise, right? And most of the devices are temperature bias dependent. So keeping constant temperature, almost constant temperature over a chip is first important point. The second important point is that if you go on increasing power, then your portable devices will be losing power very fast, and therefore you require to charge those at a very faster pace. So these are two major disadvantages of having a low power design. But the disadvantage is that when you go for low power, you also have to, your frequency of operation also starts to go down, and that makes your life difficult. So you need to optimize power and delay.
No more questions, sir.
Hello.
Sir, no more questions hereafter, I think. Yes.
I couldn't. Right. Can you? Yes. Can you repeat?
No more questions, sir. No more questions.
Okay. Thanks a lot. Thank you very much.
Thank you, Professor. Thanks for accepting our invitation. Thanks to spending your time, valuable time with us. Thank you, sir. Thank you.
Okay. Okay. Bye. Bye.
Bye. Participants, kindly be joined for the afternoon session by 2 p.m. The afternoon session going to be handled by the industry persons, Mr. Murugan. Kindly join as soon as possible.